Hey everyone, hope everybody's doing okay and staying safe. For the next few days, we're going to be working on Charles' Law. Charles' Law is a relationship in gases between the volume of the gas and the temperature of the gas, and the pressure would be unchanged in one of these types of problems. So the temperature and the volume are directly proportional. That means that as one goes up, the other will go up by the same quantity, and likewise, as one goes down, the other will go down by the same quantity. So when we express this mathematically, we use a fraction. So our initial volume and our initial temperature is going to be equal to our final volume divided by our final temperature. So you can see it's an equality, and we have our V1 and our T1 equal to our V2 over our T2. Now, there's another way to express this, and that would be using with taking the fractions out of the equation, and what we'd have to do is just cross multiply. So for this problem, what I would do is I would take my V1, so I got my V1 times my T2, and that's going to be equal to my V2 times my T1. So these are the two ways that this Charles' Law equation can be expressed. I have two problems here. I'm going to do one each way. Just you can choose whichever one you think works best for you. So when we first do any of these problems, like always, we need to make a key. Notice that it says at constant pressure. That gives us away right away that we are going to be dealing with a Charles' Law problem. But we have our starting volume, we have our starting temperature, we have our final volume and our final temperature. And what we're going to do is we're going to fill in the key, and we are going to solve for the unknown. So in this case, we have 205 milliliters of argon gas at 10 degrees Celsius. So there's our starting conditions, 205 milliliters at 10 degrees. Now, right away, it dawns on me that in any kind of gas law problem that we're dealing with, we've got to convert to Kelvin. Kelvin, if you recall, is the same increments as Celsius. It just starts 273 units different, and we have to add 273 to our degrees Celsius to get our actual Kelvin. That's the conversion. It's in your reference tables, it's in your notes, so just take a look at it if you're unsure about that. But it's 273 plus 10 for 283 K. So now we have our temperature in the proper units, that's Kelvin. Our final volume is what we're looking for, and our final temperature is 27 degrees Celsius. 27 degrees Celsius. If we add 273, it's 300 K. So there's our variables, and now we're going to plug these in. So the first thing I like to do is rewrite the expression, just so I know I'm not making any mistakes when I plug them in. V2 over T2. And then we just plug and chug. We put in the variables according to our key. So our initial volume is 205 milliliters, so it's 205 milliliters, divided by 283 K, and that's going to be equal to my V2, which is my variable that I'm solving for, divided by 300 K. 300 K. So to solve this, I just cross multiply, and I have V2 times 283 K, and that is going to be equal to my 205 milliliters times 300 K. So then I have to get the V2 by itself, so I'm going to divide this side by 283 K. That makes this 1. Whatever I do to one side, I got to do the other side. There's my 283 K over here. K cancels K. Then what I'm going to do is I'm just going to multiply the 205 milliliters times 300, and when we put that into our calculator, we get 61,500. So it's 61,500. The only units that are left are milliliters, and I got to divide that by 283, And when I do that, I'm going to put it up here because it's a little sloppy down below. My volume, my new volume, is going to be 217.3 milliliters. So all I did was multiplied the expressions on the top, that's the volume and the temperature, divided by the temperature, and that will give us our final volume. Now, if we think about it logically, we know it's a direct relationship. Therefore, as the volume goes up, the temperature should go up. So here we see, if you look over on this side here, the temperature went from 283 to 300. So our temperature went up slightly, which means our volume should go up slightly. And our problem did say that our volume went up slightly. So that is most likely the solution, as long as we didn't make a math error. So let's go down to the second problem here. I think I can, Okay, I had to pause that for a second to figure out how to move up the the document there. Anyway, so here we are. We're at our second problem, and we're going to make the key first. So I'm going to do my V1 equals my T1 equals my V2 equals and my T2 equals. And then I am going to plug in the appropriate variables. Now this says a sample of gas occupies 6 liters at STP. So 6 liters is my initial volume. I'm not going to put the decimal point in just to make it easier. 6 liters. It's at STP. Now if you remember anything about STP, standard temperature is 0 degrees Celsius, which means it's 273 K. So I'm just going to put that in there. And standard pressure is not changing here, but the standard pressure is 1 atmosphere. But we don't have to account for that because it's unchanged. It says if the pressure is held constant. So now it says the volume is increased to 10 liters. It's going up to 10 liters. We want to know what the new temperature is. Now, what's interesting about this problem is that it's solving for T as opposed to solving for V. We do the math the same, we set it up exactly the same, but I see right away that my volume has increased almost double. I mean, if it went up to 12 liters, it would be double. So I would expect the temperature to go up to close to probably, well, double would be 546 Kelvin. So it's probably going to be somewhere around 500 Kelvin is what I would expect the temperature to go up to. So let's do the math. This time I'm going to use the other expression where I'm going to be doing the formula V1 times T2. So I'm cross multiplying the original. So it was V1 T1 equals V2 T2. I cross multiply. I get V1 times T2 is equal to V2 times T1. So there's my expression I'm going to use. I'm going to plug these numbers in. I've got 6 liters times my T2, which is, 270. Nope. Be careful when you do this. Our T2 is what we're solving for. Right? So that's our unknown, and then that's got to be equal to our final volume, which is 10 liters, times our initial temperature, which was 273 K. Okay, so now I got to get T2 by itself. I divide this side by 6 liters. I divide this side by 6 liters. That's 1. Cancel out the liters. Now I've got T2 is equal to 10 times 273. And for those of you that are good at mental math, if I'm multiplying any number by 10, I just add a 0 to the end of it. So it's 2,730 K, and then it's divided by 6. Units are gone on the bottom there, so I'm just left with my now Kelvin temperature, which is what I need. And when I do the math, I take this 2,730 Kelvin divided by 6, and I get 455 Kelvin. And if we take a look, my estimate was it should be close to 500. It's not real close to 500, but that is certainly increased from 273. So I would expect that to be the correct answer, and that's how we do these Charles Law problems. So this will be posted. We're going to be working on these today, Monday, and I'll put up the answer key Tuesday, and probably take a quiz on this on Tuesday as well. So anyway, email me if you have any issues, and have a wonderful rest of your day, and stay well, stay healthy, and have a good day. Thanks. Bye.